So it's long, let me stick.
Okay.
This side, to your side of the green line.
Yeah. Okay. Thank you. So hi everybody, my name's John Evans. I spend a lot of my time dealing with traffic management and traffic engineering. So I'm going to try and give you a bit more of a practical perspective. I think there's it's quite easy to make some conclusions about traffic engineering and how you might deploy it, which are often not true in practice. So I'm going to try and use some case studies to bring out some relevant points. Just firstly, traffic engineering rather than network engineering. So assuming that we've got a defined network and that we're trying to make the best use of that network, and we have to look into how we define best, which is quite an important point. The assumptions that can often be made about traffic engineering, or there's a number of assumptions that can be made about traffic engineering. One is that to do traffic engineering, you need to use MPLS, RSVP-based MPLS TE. You don't, that's one option, but you don't have to use that. The second is that it's quite common that people undertake traffic engineering and providers actually deploy traffic engineering without having done any analysis of the actual benefit it's going to give from a traffic perspective. And the third is that there is actually quite a lot of subtle points that you really need to consider if you're looking at any of the any of the approaches to traffic engineering, and I'll touch on some of those. So I've put it out as a set of questions, and I'm going to try and address these questions. So the first one is, what's the objective of what you're trying to do? Secondly, then, are you looking to do it strategically or tactically? Which approach you're going to take? So you've got a choice of tuning metrics or deploying MPLS traffic engineering. How often to reoptimize, which is we're now getting into the points which are quite often, not obvious when you first look at traffic. First look at traffic engineering. And then if you're considering MPLS TE, there's a whole set of extra questions for that. So whether you deploy an edge mesh, a core mesh, or you do it by exception. Whether you use dynamic tunnels calculated by the head ends, or you calculate the tunnel paths themselves and specify those to the head ends. How you size the tunnels. That may sound like a really obvious question, but it's not. And then lastly, how are you going to measure the benefit of the different approaches? So firstly, the objective. Fundamental point, traffic engineering is an optimization problem. The optimization problem is you've got a fixed network and a traffic matrix, a traffic matrix being the matrix of ingress to egress flows across the network. And the problem is, how do you make best use of that network? And the question is, what do you mean by best? And typically, the optimization goals will be minimizing the maximum link utilization, considering working case. So considering when there are no link failures, for example. And the other will be trying to minimize the maximum link utilization, taking into account failure cases, which could be link failures, node failures, shared risk failures, or whatever they may be. It's important to differentiate between those, because when you analyze, which approach you might use, you'll get a different answer depending upon the goal that you're trying to target. So in terms of approaches, we've got MPLS traffic engineering. Obviously, everybody, I think, will be aware that that's an option. Also, IGP-based or IGP metric-based traffic engineering. I'll touch on that, and I'll touch on a comparison between them in terms of results. Then you've also got choices of the approach that you want to take. So, and I've defined them as tactical or strategic. Tactical really meaning you're doing traffic engineering in a reactive way. You're responding to the state of the network as it is. You're trying to relieve some congestion which has been caused by a failure or an unexpected traffic demand, and you're focused on that case. And then strategic traffic engineering, which, or what I'm calling strategic traffic engineering, which is actually more looking forwards. So that's saying, okay, well, I'm interested in making sure I've got sufficient capacity to cover these cases, these failure cases, for example. What's the best routing of traffic that I want to use now in order to make sure that I've got a good routing covering those cases that I'm interested in. So IGP metric-based traffic engineering, this is something which, a few years ago was sort of poo-pooed. I'm sure you've all done, manual metric manipulation. And, for quite a while, going back 10 years, it was assumed that, that was only any good for small bits of ad hoc changes. But there was a whole set of research done, getting on to 8-9 years ago now, which was focused on holistic approaches to metric-based traffic engineering. So actually looking to see whether it's possible to do a global optimization to come up with better routings. A number of different approaches, and we did some work looking at taking some specific networks. These are all tier ones, so they're all big networks with quite meshy topologies. And typically, metric-based traffic engineering works better in meshy topologies. But this is giving you a comparison of different approaches. So the red bar is showing just using normal IGP metrics, where the metrics set based upon the delay of the link. So that's, in the US, that's certainly the most common approach. The green is optimized metrics. So optimized, in this case, taking into account single link failure scenarios. That was the optimization goal. And the blue bar is using MPLS traffic engineering, where you are calculating optimal paths offline. So the routers aren't calculating the paths, you're calculating them offline. And that's quite an important distinction to note there, because actually if you let the router head-ends calculate the path for traffic engineered tunnels, you generally end up with a much worse answer. So in comparing them, you'll see, you get a broad range of, or you get a range when you look at the default metrics. When you look at IGP metrics-based traffic engineering and MPLS TE, you can get a difference of 15-20%. In the worst case, in the best case, you may get the same result. MPLS TE, in theory, should always be able to give a better result because you have more control. But I think the question becomes how much better is better and how much value is that to you? And then you've got to take into account the cost of deploying MPLS TE. So, having made a choice about a technology approach, whichever one it is, then an important question is how often do you want to reoptimize? And, sometimes it can be easy to assume that you reoptimize with pretty high frequency. In practice, that tends not to be the case. So, and if you look at, and this is taking one example, but if you look at the demands you've got in the network, the size of those demands, and how much they vary in time, that will then give you an indication of how quickly, how frequently you need to reoptimize traffic engineering. In this case, and this is, I would say fairly typical, or typical, the majority of the traffic was actually from a relatively small number of very large demands, which were relatively well behaved. So in those cases, as it's those larger demands that are actually causing the problem, then effectively, if you traffic engineer for those larger demands, if they're not changing enormously in time, then you don't need to reoptimize your traffic engineering with huge frequency. And it tends to be quite typical that, from a traffic engineering perspective, you're focusing in on a relatively small number of larger demands which carry the majority of traffic. So in terms of reoptimization time frame, it's days, it's multiples of days, it's not in hours. certainly I know, as an example, once a month would not be unusual, and even longer time frames than that would be, aren't unusual. I don't know anybody that's doing, I certainly don't know anybody that's doing reoptimization more than once a day. And I only know one provider doing once a day. So then if you look at MPLS, if that applies to whether it's IGP-based traffic engineering or MPLS traffic engineering. When you look at MPLS traffic engineering, you've then got a whole set of additional choices. So you've got the architecture you want to use, the architecture for the traffic engineered tunnels. Do you want to do a full mesh from all your edge devices to all your edge devices? Well, that becomes quite a burden. It's an n-squared problem. It becomes quite a burden as you've got a lot of edge devices. An alternative is to do, if you like, a core mesh to bring that in and just control the core from a traffic engineering perspective. Clearly reduces the number of tunnels. Does suffer its own problems in that with traffic engineering, as it's deployed in most deployments, the traffic engineered tunnels aren't advertised as links into the IGP. So what happens is, a packet gets to a head end just using normal routing, normal IGP routing, and then it happens that on the head end you're saying, rather than using a default path, stick this packet in that tunnel. A consequence of that is that if you have a failure and tunnels shift around the network, you may actually have packets shifting to which tunnel they're going into. And you can end up with situations where your tunnels are wrongly sized for the packets going into those tunnels. So, that's an issue with a core mesh. If you do edge-to-edge tunnels, that doesn't happen. But that can be overcome. You can use as a function called forwarding adjacency, where you actually advertise the tunnels into the IGP for outside of the traffic engineering domain, if you like. And then a final approach is just to look at on a per exception basis. Focus on the bigger demands that are causing the problems and actually route those over paths in order to make more effective use of capacity. So looking at another example, and this is a similar, I guess a similar data point to the previous one. This large global provider, this was looking at the European network, and effectively what you've got is a matrix of source destination, and the colouring is showing you effectively the size of the demands. The more red, the larger the demands. And again, similarly to the last case, the majority of the traffic was made up of a small number of very large demands. So in this case, the right approach wasn't to do a full mesh of traffic engineered tunnels, or rather you could have done, but that would have been a big overhead, a lot of tunnels, big administrative burden, when really the focus was on a relatively small number of those big demands. And so, a core mesh or doing it on exception would have probably been the most appropriate in this case. So, you've decided which technology approach. If you're taking MPLS TE, if you decided the way that you want to deploy it, next question is, how do you set up the traffic engineered tunnel paths? Now, it's often assumed that traffic engineering, MPLS traffic engineering, is just like ATM VC routing. You turn it on, you don't really worry about it too much. But that's really not the case, and it's not it's really not the same thing. What are the differences between dynamic routing and explicit routing? Well, dynamic routing is where the head end, or dynamic path options and explicit path options. Dynamic path options are where the head end router, the router that's the source of the tunnel, calculates the tunnel path based upon its view of the network. Okay. Well, that sounds okay. What might be wrong with that? Well, its view of the network's the same as everybody else's view of the network, so shouldn't they, come to the right solution? Well, the answer is no, not necessarily. If you imagine, imagine the scenario that you've got two links. One of them is 1 gig, and the other one is 10 gig, and you have two tunnels. One of them is 1 gig, one of them is 10 gig. If the 1 gig tunnel is set up first and is set up over the 10 gig link, then the 10 gig tunnel cannot be placed. So, now in that case, what you'd really want to do is move the 1 gig tunnel and then be able to set up the 10 gig tunnel over the 10 gig link. But routers on their own won't come to that conclusion because they just look at what's available and set up their tunnel. So you get sequencing issues, and that's what's called if you like, the tunnel packing problem, is that they don't come to the most efficient distribution of traffic because they're all routing their own tunnels based upon their view of the network, and you can have issues due to that sequencing. So an explicit path option is where you've got some offline system that's looking at the whole problem and is able to come up with a more optimal solution, determines a tunnel path, specifies that to the head end, and then the head end just deals with the signaling of the tunnel over the path that it's been told. What are the characteristics of that? Well, you can come up with a more optimal solution from a bandwidth management perspective, but you do need some offline system that's calculating your tunnel paths. This is an example. This is showing DT. And this is showing the analysis of the different approaches in their network. And so what I'll just highlight the different approaches. And if you see here, what we've got is we've got the the maximum utilization in taking into account failure cases. So if you like, the worst case utilization is what's shown here. Whoops, go back. And we've got the normal case highest utilization here. So this is working case maximum utilization. This is failure case maximum utilization, picking out the highest utilized links from the network. So you can see up here we've got dynamic MPLS TE tunnels. That's the head ends calculating the paths themselves. So to support the traffic that they had, you can see that you end up with a solution where, in the worst case, actually you've got 100% utilization in normal case and 180% in failure case. So, a far from optimal solution when you consider the other results. So then, we look down here, we've got this point here, this brown dot here, which is explicit primaries and secondaries. That's where something offline is calculating the tunnel paths and specifying to the head ends where they should be. And you can see that, that green point is the theoretical best you could get with the traffic they had on the network they had. So that comes pretty close to, being optimal. The blue line then represents what you could do with IGP metric-based TE. And this is, up here you've got optimizing for working case, and you can see that reduces the utilization in working case down to 50%, the worst case, which is great, but the failure case utilization is up at 180%. So, clearly if you're optimizing for the working case, you're suffering there in the failure case. This blue point here represents optimizing primarily for failure case, and you can see that the working case utilization is higher, but the failure case utilization is more. The working case utilization is higher, but the failure case utilization is significantly reduced. In this case, what they went for is another optimization goal, which was prioritizing failure case, but using IGP metrics. So it's sort of getting them to that point there. Another example illustrating the difference between some of the different approaches. So different network, and in this case we've got 4 lines. One was default metrics, which is the black crosses, which you can maybe just see here. It's probably easier to look at the deck, but it's the black line. Excuse me. And then we've got MPLS using dynamic tunnels with the head ends calculating the paths. Then the blue line represents metric-based TE, and the green circles represent explicit traffic engineering. And the thing to point out is that a couple of things to point out. So one is that both metric-based TE and explicit traffic engineering tunnels can both get to a point when you look at failure case where they're bringing the utilization down to below 100%. So to some extent, if that's your target, they're both successful. How do they? The other two approaches don't. Neither of the other two approaches did. But how do the approaches differ? Well, if you see the green line here, it kind of goes more horizontal to over a greater number of links, and then you've got a bit of a climb at the end, which is basically showing that they've managed to reduce the utilization of more links across the network, and you've got a few that are more highly utilized. Whereas metric-based TE, you know, you've got this difference here, shows that these links are higher utilized. So you've got a less optimal distribution of traffic. Does it matter? Well, probably not, because really what you're interested in is the worst case, and you know, how highly loaded those most heavily utilized links are, which is that point there. Next point is to look at tunnel sizing and how you set tunnel bandwidths. Now, that might seem completely obvious. You know, you set the bandwidth of a tunnel to be equal to the traffic that's going into it. But it depends how you define the traffic going into it. A tunnel is not a physical link, and traffic, you know, has an average rate and a burst characteristic. And so do you set the tunnel bandwidth to be equal to the peak of that traffic? Do you set it to be the average? Do you set it to be a percentile? If you get it wrong, you know, if you set tunnel bandwidths too high, you might, you know, have tunnels that fail to be set up, even though you've got capacity. If you get it wrong, you might have, if you could set it too low, you might have situations where you have congestion, but you do have capacity somewhere else. So tunnel sizing is not, you know, it's actually quite important. Two approaches you can take to tunnel sizing. One is the head-end routers set the size for the tunnel based upon what they've seen, based upon the past history. That has a few issues. One is that obviously that's based upon history, and what happens in the future may not be, you know, may not be quite the same as what happens over the last interval. And setting that time interval is quite important. I've got that in the next slide. Second is that tunnel bandwidth set by the head end is not persistent, or generally not persistent. So router vendors aren't saving what the tunnel bandwidth for when they come up again, because you may have a different routing state if you have a problem and then come back up. And then the other approach is to, you know, is to again have something offline that tells the head-in routers what bandwidth the tunnels should be. Now, if you're using explicit path options, if you're telling the router the path tunnels take, it doesn't matter. Because if you're saying, for this tunnel, go from A to B to C to D, it doesn't matter whether you're setting that tunnel to be 10 meg, 100 meg, 300 meg, because you've set the path. And the function of the tunnel bandwidth is just so the router can calculate the path. If you're telling him the path, it's irrelevant. If you're using dynamic path options, then our recommendation would be for those tunnels to set the tunnel bandwidth to be the same quantity that you would use effectively for capacity planning of those demands. So, you know, and typically that would be something like the 95th percentile of the samples over, you know, over the period of interest. Just one. This is another example showing an issue with having the head-end routers set the tunnel bandwidth, and this is where, in this case, you know, it was being done on a every couple of hours basis, and as you can see, this is what's happening with the traffic, and then this is what's happening with the tunnel bandwidth, and you can see that because the router's setting the tunnel bandwidth based upon the traffic in the past couple of hours, effectively, you know, what's being set for the tunnels is lagging what's actually happened. So, you know, once you've gone past your peak and the traffic's dropping off, your tunnel bandwidth is still at peak. And then when you start ramping up, your tunnel bandwidth is lower than peak. So that's an issue with using, you know, with just using the past couple of hours history. So, you know, and that has been done in the past, but typically I would say, you know, no less than a day as being the interval over which you're doing the optimization. If you are doing the sizing, if you are doing dynamic sizing by the head end. Okay, so that was pretty much it. It was a fairly whistle-stop run through. Just in terms of a quick summary, you know, very important to decide what you're optimizing for, failure case or working case, because that will give you a different comparison on the options. You have a choice of tactical, strategic, IGP-based versus RSVP TE-based. With RSVP TE, you get the choice of edge mesh, core mesh by exception. Explicit paths, rather than letting the router calculate the paths, is definitely gives you a more deterministic, more optimal answer. And also offline sizing gives you, a more deterministic answer. And in terms of reoptimization and resizing, it's orders of days, it's not orders of hours. Last point, which I had in the first slide, which is how do you actually determine, if you want to compare one approach against another, how do you do it? And I mean, the important thing is that if traffic engineering is sort of here in a planning process, you've got stages earlier that you have to do in order to understand whether you're going to get a benefit from traffic engineering. So, firstly, you've really got to understand your traffic. You've got to understand your network traffic matrix and what the routing of that traffic is in normal case, even to be able to understand whether you're in fact going to get any benefit from traffic engineering at all. And quite often, it's quite often you see situations where people don't have a really great grip on this when they start doing traffic engineering. That was it from me. Any questions?
Hi, Adrian Farrell, IETF Routing Area Director. So, we've been bashing on about traffic engineering in the IETF since I was a young girl, and I'd like to know how much you think it's deployed and why.
Yeah, it's a very good question, and so I think if you go back a few years to when traffic engineering first came out, there were very few providers deploying it for the reasons of traffic engineering, MPLS TE that is, and the majority of deployments were for fast reroute. I think from my experience, what's happened now is with MPLS TE, a whole area of the emerging markets have assumed everybody does TE, and they've deployed TE and are doing some of these things which haven't really been deployed elsewhere. So it's kind of strange that you had, TE being widely deployed for fast reroute, not that many people, this is MPLS TE, not that many people using it for traffic engineering reasons, and then, a whole sectors of the market have assumed it is being used for traffic engineering reasons, and they've gone and deployed it. And also some vendors' architectures use it as, it's an implicit of their architecture, certainly with, in access infrastructures. So I think what you've had is, with a perception that MPLS is becoming the norm and the de facto amongst service providers, which is a perception in some parts of the market, that's led to a much bigger deployment. But I would say that in a lot of cases, it's done without really a great understanding in a lot of cases of some of these issues and what's happening.
What's your perception on, if you can say just a few words on IEEE and Metro Ethernet Forum work in this same area, which is traffic engineering and service provider networks?
You mean the
MAC and MAC,
the PBBTE stuff?
Yeah.
I think I'll give I think as a software vendor, I can probably be agnostic to some of the router vendor discussions. I think in reality, that's a push. It's a disruptive market push to position a different set of products in the same space. So for those that aren't aware, PBBTE is doing, rather than doing a label stack, which is done in MPLS, where you've got a packet, a label, it's doing the same with with MAC in MAC, which is two Ethernet headers. So it's doing packet, Ethernet header, and using the RSVP TE control plane to set up if you like, the bridging. I think personally, it's a sort of disruptive vendor market play to try and insert their products into a space. In terms of how it affects traffic management, it's the same set of capabilities, so I don't think it has a huge impact.
Have you seen any significant size deployments of this kind of technology?
I've seen none, and you know, maybe quoted out of context, but but I think the main protagonist for that was Nortel, and the main provider pushing it was BT, and BT. There's maybe somebody from BT here, but BT announced formally that they weren't going down that path anymore, and I think we all know what's happened to Nortel. So I'm not aware of any implementations of that, and certainly from my side, we're not being asked to do anything we've not been asked to do anything in any of those environments.
Thanks.
Keith, was there a question on RSA?
No.
No? I think there was. Oh, I'll find it. The question was that somebody would be interested to hear what your opinion is on whether your approach actually is trying to guarantee quality through only one means, whereas one can simply use TE to provide more optimal paths, but QoS handles anomalous flows.
Yeah, so traffic engineering and quality of service are to some extent, they're orthogonal tools to the same problem. If you're looking at delivering SLAs, the problem always comes down to managing capacity. And if you haven't deployed diffserv, you're managing capacity on aggregate. If you've deployed diffserv, you're managing capacity per class. And so, when you look at traffic engineering solutions, they are just another tool set in the problem of managing capacity. So I think actually both things go together. They're not necessarily things in isolation. And when you look at your optimization goals don't have to be optimization goals on aggregate. You can also look at optimization goals per class. And that doesn't mean you end up with a different solution for each class, but that may mean that you come up with the solution that is meeting the SLA requirements of the class that has the tightest requirements. So it's definitely what I'm discussing here isn't an alternative. The two things can be completely used together. Okay. Thank you very much.
Thank you, John. So, going back to our agenda, it's wrap-up time, and we're basically 5 minutes behind schedule. Sorry. So, that's great. I really appreciate the contribution of all the speakers. We've had some great presentations today. It's been nice to have a couple of themes to hang things around. There's been some pretty substantial content as well. So I think we should all thank all our speakers for the contribution today. So before we finish completely, there was just a couple of things that I wanted to share with you. If we go to the bottom of the attendee list, Tom has gathered some stats for us, and I've just made some notes as well. So we had 89 people register for this meeting, which for an out-of-London meeting, I believe is the highest number that we've had register. We've had 73 people viewing the webcast, which is quite impressive, really. You can see the webcast stats here. I think it's testament to the job that Tom and Brandon and various other helpers do behind the scenes to make the webcast happen. So, I think we should show our appreciation for Tom and his colleagues' efforts in that. The downside is the webcasts are so good, we get less people at the meetings and there's less people to buy beers afterwards. But I think it's really good that people can rely on attending UKNOF meetings, even if they can't be here in person. So I think we had about 65 people actually show up. So, well, it's January. So it's not really surprising. 47 people in IRC, 9 via Jabber. So obviously there's overlap between these, but that's a pretty respectable attendance. The other statistic that we have, which I've bodged onto another place in the website, is the actual traffic. So this is how much traffic has been pumping in and out of here during the day. The bottom graph is IPv6 and the top graph is IPv4. So it's quite interesting that there's quite a lot of time there's more IPv6 than IPv4. But again, you know, it's great that all the connectivity has just worked. Big thank you to Andy and to Dave and various other people for their efforts in getting that set up yesterday, and a big thank you to all the Zen team for setting the connectivity up so that it all does just work for both the webcast and the actual keeping you all connected to your operational crises back home. So thank you for that as well. So that's pretty much it. There should be 3 taxis at reception in about 5 minutes' time for those of you who need to get to Rochdale Station. What else? Yes, I think that we should thank the curry organisers last night. I wasn't completely sure who finished up organising it all, but Dinesh and Andy were definitely in there. And I thank you to Dinesh and Sheena for their efforts in doing all the admin for the meeting. So I think that basically we're done for this time. We've got dates fixed for the next 2 UK North meetings, April the 22nd in London. As I say, we have some tentative sponsors. We need to find a venue. But if we can get some firm sponsor offers, that would be great. Edinburgh on the 7th of September, just after the festival, so you can have some fun in Edinburgh before you go to the UK North meeting. And for that we have a host, but again we're looking for sponsor support for that. And obviously for both of these meetings we're looking for more speakers or ideas for presentations or ideas for presentation themes and topics. So with that I think we're done. So thank you all and see you next time.
So